Hello, this is Wendy, and this is what I came up with to answer the questions for the final exam. So, to start off the semester, one of the first things we learned was the axiomatic method. This is basically making sure that the conclusions we made are true and understood by all parties. When we can prove the conclusions logically and using propositions, theorems, definitions, and so on that we have already previously proved and defined, or in our case for chapter 1, came up with undefined terms. So as I said from the beginning, we only use terms, definitions, theorems, etc. that we've already proven or defined. So that means that we could not say that a rectangle exists because Euclid's fifth postulate did not hold in neutral geometry. It was only when we assumed other theorems when that we have already proven that we could say that a rectangle exists. So one thing that the axiomatic method did was that it played a huge role in our class because we built upon all the things that we had already learned. And one of the ways that it was really helpful was that it prevented assumptions from the diagrams or things that we can see in the physical world. So for incidence geometry, this geometry is basically only using lines and points. It is like only having a pencil and a straight edge to do constructions for proofs. That means that circles, ellipses, curves, etc. do not exist because we cannot prove those concepts only using straight lines and points. Incidence geometry provided the first set of axioms that filled in the gaps for Euclid's postulates. Speaking of Euclid, his first four postulates were good, but it was not sufficient enough to prove the things he claims to have proven. There is a need to expand his postulates and definitions because he assumed certain facts because they were obvious. As noted in our book, it took 3 incidence axioms to strengthen Euclid's first postulate. Another advantage in expanding Euclid's postulate is that it provides the consistency and structure of the axiom system. And the axiom system is basically all the axioms that hold in neutral geometry. So incidence axioms, betweenness, congruence, axioms, parallelism, and continuity. We know that incidence geometry, as well as betweenness and congruence, is consistent, and that is why it is important for our axiom system. Although incidence geometry provides a better foundation than Euclid's 4 postulates, there are still some holes in it. First off, a point lying between 2 points is not defined. This comes later when betweenness is introduced. Furthermore, Euclid's third postulate will be a struggle since circles cannot be drawn only using a straight edge. Also, congruence is also not mentioned, so Euclid's fourth postulate would not be able to be proved with the 3 incidence axioms. The betweenness and congruence axioms are just as important as the incidence axioms. They're also needed when doing regular Euclidean geometry. So now that we have moved on, let's assume that we got our betweenness and congruence axioms. So I just wanted to mention that we need these groups of axioms as well as continuity and parallelism for neutral geometry because they are all independent of each other. So that means that you cannot, the incidence axioms do not help betweenness because it's different. Yeah. So while both of these are important, I will only discuss the betweenness axioms' importance in neutral geometry. The first 4 axioms of betweenness are stated below. With these 4 axioms, there are many propositions and theorems such as the crossbar theorem and Pasch's theorem that come about. These propositions and theorems following these axioms are important for neutral geometry because it provides more propositions and theorems, and it also helps when a line has more than 3 points. It would be easy to say It would be easy to define betweenness if all lines only had 3 points A, B, and C, but we know that that is not the case because there are infinitely many points between 2 points. The fourth betweenness axiom also assures that we are working on a two-dimensional space. Betweenness seems very obvious, but it plays a role in consistency in our axiom system. It is also neutral geometry because we cannot assume things we already know. Or it also helps in neutral geometry because we cannot assume things we already know. This further strengthens our conclusions. It is also helpful for proofs of alternate interior angle theorem, exterior angle theorem, midpoints, etc. that we see in Chapter 4. So the only thing that isn't proven in neutral geometry, without assumptions of course, is that a triangle is 180 degrees in Euclidean geometry. But in hyperbolic geometry, it is less than 180 and it's greater than 180 degrees in elliptic geometry. This brings up the next question. How does this relate to Sacchari and Lambert quadrilaterals? Well, this affects Sacchari quadrilaterals because there's only a guarantee that there are two right angles, the base angles, in a Sacchari quadrilateral. The only time that the summit angles or top angles will also be right angles would be in Euclidean geometry where rectangles exist. Other than that, the two summit angles are up for debate to either be obtuse or acute. I say that they have to be obtuse or acute because of proposition 4.12 part A, Sacchari 1. In elliptic geometry, the summit angles would be obtuse, which you see in the second picture. In hyperbolic geometry, the summit angles would be acute as shown. For Lambert quadrilaterals, there are three right angles and one unknown angle. The unknown angle is right if we assume Euclid's fifth. Otherwise, the unknown angle would be obtuse in elliptic geometry and acute in hyperbolic geometry. We know that the angle being acute, right, or obtuse in the respective geometry because of the uniformity theorem for Sacchari quadrilaterals and its corollary one for Lambert quadrilaterals. So as I said, so if the unknown angles in both Sacchari and Lambert quadrilaterals would be acute in hyperbolic geometry and obtuse in elliptic geometry, and this would be the same because of the uniformity theorem. So going on to question 5, the most important thing that not the most important thing, the most interesting thing that I had read about was Clairaut's axiom. So mostly a lot of mathematicians try to prove Euclid's fifth. And I thought that Clairaut's axiom was the most interesting because it was a basic sentence and it was rectangles exist, but it has many consequences and assumptions behind it. I think it is very interesting that Clairaut used physical quadrilaterals to justify his axioms. He did not take into consideration other geometries such as hyperbolic, where rectangles do not exist. It is also interesting when the text noted in page 219 that if a rectangle can be drawn on the ground, then you cannot believe that the earth is spherical, which made me think for a minute and picture the quadrilateral and elliptic geometry. So for the statement mentioned, what I interpreted it to be was that if Euclid's fifth postulate was proved, then Euclidean geometry would be inconsistent. If we suppose that Euclidean geometry was consistent, then the fifth postulate can be proved with the axioms that we have. But since the neutral geometry axioms cannot prove the fifth postulate, then the fifth postulate would be false, or unprovable. Thus, we have the fifth postulate can be proved, and it cannot be proved in Euclidean geometry, which leads which leads to a contradiction. Therefore, the conclusion is false. So basically, to sum this up, because it is a lot of words, if the Euclidean geometry was consistent from the beginning, then adding another axiom would not make it consistent, but this is not the case when we want to prove the fifth postulate. And then something fascinating that I will always find fascinating is how many years it took to accept irrational numbers, negative integers, and the number 0. It is something that I never thought about before I took this class. I didn't realize how controversial these concepts are, and something that I don't take for granted anymore. Imagine how different math would look if we had always denied the existence of these concepts. Yes, and that is something that I love to tell people. I know that I had told my little sister probably the day after I read about it. And then, just to sum things up, I want to say thank you, Dr. Williams, for taking a chance to teach this class. I will be grateful that I took this course now instead of fall 2021. Have a blessed winter break and next semester, and I really wish you good luck teaching hybrid again. Thank you.